Okay, so in the previous class, we have gone through this circular tanks with flexible joint between the floors and the wall, and then we solved one example related to the flexible joint between the floors and wall. Okay. Today we'll see circular tanks with rigid joint between the floors and the wall. We'll first go through the theory part, and then in the subsequent lectures, we'll take examples related to circular tanks with rigid joint. So let us go through the background. So let us consider a tank section. These are the walls. Let this be the floor or base of the tank. So this is consider any tank section, and let this be the diameter. Let it be the height of the tank. Let D be the diameter and H be the height of the tank. And let us consider this point as A and this as B. If you see the deflected shape of tanks with rigid joint, here I'm showing this detail. This is a rigid joint. Rigid joint. Okay, that means either it is fixed or it is a continuous joint. So deflected shape of it will be, since it is free at the top and fixed at the bottom, so it will be just like you can imagine this is a cantilever. So this will be the deflected shape, and if this point is uh, this point let it to C, okay, this is A, this point, okay, and this point to B point. So and this point, the deflected one, with C dash. Okay. Now, if you see the pressure diagram for this tank, it will be triangular with maximum pressure at the base. Okay. And the intensity of this pressure the intensity of the pressure at the base is gamma W, that is the intensity of the water times H. Okay. This is the pressure intensity at the base. And, since this wall deflects like a cantilever, we can say that at this point your deflection is zero. At this point, your deflection is zero. Your bending moment is also slope is also zero. On this side, your deflection is zero and slope is zero. Okay. And at the top, again, your bending moment will be zero. Okay, and your shear force will be zero. Okay, this is for the uh, free at the top, free at top, and fixed or continuous at bottom. Okay, so since this is fixed at the base, the deflection will be zero and slope will be zero. You can see the deflected shape. The deflection is zero and slope is zero. And at the top, the bending moment and shear force will be zero. Okay. This is the tank section, circular tank section with the rigid pipe. Circular tank section with rigid joint between floor and walls. Now, for uh, deep tanks, means the depth is more for deep tank. For deep tanks with small diameter, that means your H by D ratio is much greater, or we can say H is much greater than D. For deep tanks with small diameter, uh, these tanks in these tanks the hook tension will be predominant, and the cantilever action will be very small. See, when you have rigid joint uh, between the floors and wall, uh, there are two condition predominant forces, or we can say predominant actions. One is hook tension, and another is cantilever action. So now, if your tank is deep and the diameter is small, in that case, the hook tension is predominant. Hook, hook tension is predominant, and this cantilever action is very small. Very small. Cantilever action means a very small amount of the force will be resisted by horizontal shear. That is very small amount uh, amount of force is resisted by horizontal shear. Okay. Now, another case for small for small tanks with large diameter, or you can say for shallow tank, for shallow tanks with large diameter, means you can consider, see, this tank will be like this. Means it is very deep, and the diameter is very small compared to the depth. If, whereas in this case, the diameter will be very large and the depth of the tank is small. Okay, so in such cases, your H is much less than B. In that case, the cantilever action is predominant, and hook tension is very small. Hook tension is very small. Here we mean to say that the resistance due to hook tension is predominant. Okay, this is resistance due to hook tension is predominant, and resistance due to cantilever action is very small. Same here also, resistance due to cantilever action will is predominant, and the resistance due to hook tension is very small. Okay, and for medium tanks, both the actions will be acting simultaneously. So for medium tanks, we have hook tension plus this cantilever action. Okay, so with this, let us derive a formula to find the bending moment at different heights of such tanks. So for that, let us consider the same tank section. And let now let us consider any arbitrary section at depth x. Okay? So at this x distance, let the pressure at this level will be gamma w times x. Okay, because at this that the pressure will be due to the water above that section. So it will be gamma w times x, and this pressure is resisted by the cantilever action and the hook tension, that is the radial pressure. means it will be equal to the cantilever pressure due to cantilever action and due to the radial action. And let T be the thickness of the wall. So, write different terms. Here, your PC is the pressure per unit area transferred by cantilever action. By okay, and PR is the pressure per unit area transferred by hook tension. Now let T be the thickness of wall. I be the moment of inertia. Moment of inertia per unit length, and this can be taken as dq by 12 into 1 minus mu square. Now here for per unit length, we remember it is bdq by 12, but it is per unit length, so it is dq by 12, and this term accounts for the effect of the lateral deformation or lateral strains. So this is considering effects of lateral strains. And this is mu is the Poisson's ratio. Mu is the Poisson's ratio. Let gamma be the unit weight of water, unit weight of a liquid, unit weight of liquid. In this case, it is water. And T be the root tension. And T equals to modulus of elasticity of concrete. Modulus of elasticity of concrete, and Y R with the radial expansion, radial expansion due to this pressure PR, due to this pressure PR, due to pressure PR, and let YC be the outward deflection, outward deflection due to PC, that is due to PC, which is pressure due to cantilever action, that is due to cantilever action. So with these terminologies, now let us derive the expression for the bending moment. Now, at any height x, that this at any height x, at any height x from top, your gamma w times x pressure, the pressure will be equal to uh, pressure at x is equal to gamma w times x. Okay, this thing. Okay, that is gamma, and which is equal to Pc plus Pr, and this is equal to Pc plus Pr. That is pressure due to Conti direction and due to hook tension. Now, from the definition of the hook tension, the hook tension at any depth x from top is equal to Pr times d by 2. Okay, so pressure into the half the diameter, that will give you the hook tension. So hook stress is equal to Pr d by 2 into t. Okay, and the corresponding hook strain is equal to Pr d by 2 t into e. Okay, see, if we remember, the E is equal to stress upon strain. So we are finding strain. So strain is equal to stress divided by modulus of elasticity. So we are dividing this stress divided by modulus of elasticity. So now the radial expansion at height x from top is equal to YR as per our definition. The radial pressure due to the hook tension. Okay. So the drop is equal to YR, and this is equal to and this produced by actually hook stress. This is due to the hook stress. Okay, so it will be equal to hook strain multiplied by radius. So the hook strain is Pr d by 2 P e into the radius is d by 2. So it can be written as Pr d square upon 4 T e. Okay. So in terms of we can write in terms of PR. Okay, let us transform this in terms of PR. So your PR is equal to 4 T E 4 TE into YR, that is the radial pressure, radial expansion divided by V square. Okay. Now from compatibility, the expansion due to radial pressure should equal to the expansion due to the deflection due to cantilever action. So for compatibility, this has to be equal to O T E, let y be the deflection divided by d square, because for compatibility, YR is equal to YC, that is the radial expansion should be equal to the deflection due to cantilever action, and let this value be some Y. Okay, so let us mark this as number 1. So in this equation, you require the value of PC and PR. So we have the value of PR in terms of the deflection Y. Now for this term PC, we'll now use the simple bending theory to run simple bending theory. We know that the bending moment is equal to EI d square y by dx square. Okay, and the further derivative of this will give you the shear force, because we know that C m is equal to EI d square y by dx square. You know that, then you know that the shear force V is equal to dm by dx. Okay, means the derivative of the moment with respect to x. So that will be EI g cube y by dx cube, and the further derivative of shear force will give you the load intensity, that is dv by dx. So that will be EI d raised to the power 4 divided by x raised to the power dx raised to the power 4. So here the first derivative, this is the bending moment equation. Bending moment equals to EI d square by dx. Shear force is equal to EI d cube y, this one, d cube y by dx cube, and your load intensity, or load intensity, uh, let it be PC is equal to load intensity PC is equal to EI d raised to the power 4 y by dx raised to the power 4. Okay, so here this, because this is due to bending theory, so this deflection will be actually the deflection due to cantilever action. But from the compatibility, we know that this yc is equal to yr, and that is equal to some deflection y. So it is equal to EI d raised to the power 4 y by dx raised to the power 4. Okay, now from number 1, from equation 1, this PC plus PR equals to gamma W x. PC plus PR is equal to gamma W times X. So now we have the value of PR, so we can substitute that. So this implies PC is equal to gamma W X minus PR. Okay, so PC is equal to gamma W X minus PR. Now what is PR? PR is 4T E Y by D square minus 4T E Y by D square, and this should be equal to this. Let this be number 3, because here PC is equal to EI. This should be equal to EI T raised to the power 4 divided by dx raised to the power 4. Now, now we can arrange this in the form of d raised to the power 4 by dx raised to the power 4. Okay, we divide this EI term on both the sides, so it will be uh, d raised to the power 4 d4 y by dx raised to the power 4 plus 4 t e y divided by d square into ei. Okay, so this e and this e gets cancelled. This should be equal to gamma w times x by ei. Okay, and for simplicity, let us write gamma w into gamma w is equals to w, means any liquid, whether it is a water or any, it can be. So, or can write this as d raised to the power 4 by dx raised to the power 4 plus 4t by id square times y is equal to gamma times x by ei. Uh, Let us take gamma w is equal to any liquid density in general. So this is the uh, differential equation. Okay, and this is of the form, if you remember from the mathematics, this is of the form y raised to the power 4, means the fourth derivative of y with respect to x plus some constant k into y is equal to c. K to the power 4 raised to the power, this is of the form of this. And the solution of this expression, the solution of this expression is equal to y is equals to e raised to the power kx times a sin kx plus b cos kx. Okay, uh, this plus e raised to the power minus kx times c sin kx plus d cos kx plus c by 4 k to the power 4. Okay, so this is the solution for this this differential equation. So what we can do, we can transform this differential equation in this form, and we can have the solution in this form for this expression. So, let us take taking uh, this 4t by I d square equals to k to the power 4. If you take this, then this expression is analogous to this standard differential equation. Okay, and we can have the solution in this form. So your expression becomes d to the power 4 dx to the power 4 plus k to the power 4 into y is equals to some constant c, which is equal to gamma x upon di. Okay, see this c and this c is different. This is some constant c. Okay, and this is another c. Okay, let us designate this with a small c. This will be the small c. So the solution for this expression is now y is equals to e raised to the power ax, where k is 4t by id square. We substitute the value uh, of k to the power 4 is equals to 4t by I d square into sin a sin kx plus b cos kx plus e to the power minus kx c sin kx plus d cos kx plus small c divided by 4k to the power 4. So this is the solution. Now to solve this, we need four boundary conditions because we have four unknowns. This is first unknown, second, third, and fourth. So four unknowns, we require four boundary conditions. So the boundary conditions are depending on our cases. So uh, the same expression you can use for the walls with fixed heat as well as the walls with hinged joint with the base. So let us take the first case, uh, that is walls with fixed base and free top and top, free at top. Okay. So for this condition, the first expression is at x equal to h. X equals to h means when x is equal to h, that means at the base. Okay, this is base and this is top. Okay, so when at x equals to h means you are at the base, that is at base. Uh, what is the condition at base? At base, your this delta is 0. Okay, and means your deflection is 0 and slope is 0. Okay, at base, these two conditions. Okay, so you are at the base. So at base, the reflection is 0. So at x equals to h, y is equals to 0 because deflection delta is equal to 0. Second condition is at x equals to h, again at base. Second is your slope is 0. Okay, your slope theta is 0. Now slope can be written as, you remember slope is nothing but your first derivative of deflection. So it is dy by dx equal to 0. Then at x equals to 0, that is we are at the top. Okay. Uh, so at x, you put the value of x, you are at the top. So at the top, bending moment is 0 and shear force is 0. So at the top, your bending moment is equal to 0. Okay. And from the expression of bending moment, okay, so bending moment is the second derivative of the deflection. See, from this, bending moment is the second derivative of the deflection. So your uh, slope is equal to 0. Here m is equals to 0, which is nothing but your d square y by dx square is equal to 0. So we can write here the second derivative of y with respect to x is equal to 0. Then uh, this was the third condition, and the last fourth condition at x equals to 0, that is again at the top, your shear force is 0. Shear force is equal to 0. So shear force is equal to 0 means the shear force is the uh, third derivative of the deflection. Okay. So which is d cube y by dx cube equal to 0. So it is d cube y by dx cube equal to 0. So for this for fixed days and feet of using these four conditions, you can get the values of these four unknowns. This A, B, C, and D. And substituting these values, you will get the solution. So your solution now becomes y is equal to gamma times x divided by 4 e I k to the power 4 plus a sin kx e to the power kx plus e to the power minus kx plus cos kx e to the power kx plus e to the power minus ax minus 2a e to the power minus ax cos ax. And your bending moment at any x, this is y at any x distance at any y height, uh, this deflection at any height x, and this moment at any height x is equals to, we know that it is ei uh, d square y by dx square, d square y by dx square. So can be written as minus 2 ei k square a cos kx into the power into e to the power kx plus minus e to the power minus kx minus b sin kx into e to the power kx minus e to the power minus kx minus 2a e minus kx into sin kx. Okay, so this is the expression. Now you know that here e to the power kx plus or minus e to the power minus kx is equal to e to the power kx, because e to the power minus kx is very small. So compared to e to the power kx. Okay, uh, so you can finally substitute this condition and the above conditions to get the solution. Okay. Also, you know this mx equals to minus ei d square y by dx. So this is the expression for the moment. You equate this moment equal to 0 and put the value of x equals to 0, you will get one expression. Same way, you derivate this moment expression one more time, then you will get the shear force, and you equate this shear force expression to 0 and substitute the values of x equal to 0, you will get another expression. Then and at x equals to h, you substitute the values of h in the first this expression. Let this be number 4 and let this be number 5. Then you substitute the values of x equals to h here, you will equate it to 0. You will get the corresponding expression to first condition. In this fifth expression, you substitute the value of x equals to 0, you will get one another expression. Then you derivate the fourth expression one more time and equate to 0 and substitute x equals to 0, you will get one more expression. You derivate the fifth expression one more time, you will get this shear force and equate it to 0 and substitute the value of x equals to 0, you will get one more expression. So out of all these four expressions, you will get the values of the unknown. Okay, so this is how you can solve the tanks with fixed space. Now suppose the tanks is having hinged base. For hinged base, This is called the fixed base. Fixed base and free top. Now, second is hinged base. Hinged base and free top. So in this condition, for free top, the bending moment is zero at the top. Shear force is zero at the top because it is free top, because it is free top. Now at the base, since it is a hinged joint, hinged at bottom, the bending moment is equal to zero, and your deflection is also equal to zero. So only difference is instead of this slope, equals to zero, you substitute the bending moment equal to zero, you will get the condition for the hinged base. Uh, and for fixed or continuous base, these are the conditions, and for hinged base, these are the conditions. So same way, second case, case 2, that is walls with hinge base. Hinge base and free at the. So the conditions are same except the one condition. So at base, at x equals to 0, instead of this, at base, your bending moment is 0. So here it would be d square y by dx square. So d square y by dx square is bending moment is equal to 0. And d square y by dx square. Why? Because hinge at base, hinge to the base. Okay, so this is the general expression. You substitute the conditions. Okay, the general solution. You substitute the condition, you will get the corresponding uh, expression for the deflection as well as the bending moment at any height x. And then you can form a table to get the uh, uh, values of the bending moment and deflection at any height x. Now, I guess IS-7370 part 4, it gives this value, gives values of bending moment at any height x, bending moment at different height. Right? These are based on the elastic curve, based on theory of elastic curve. Theory of elastic curve. Okay? So you can use either the tables given in IS-7370 part 4, or you can derive the expression in this way, apply the boundary condition, and find the expression and substitute the values of those expressions to get the bending moment at different height. Okay, but this using this part 4, there are direct tables given which you can use. A sample of this I can show you. So the samples of these are given in the material I have provided to you. Okay, so such tables are there for different this x square by dt ratio. You can get the values of the bending moment at different heights. At 0 height means at the top, at 0.1 h, 0.2 h, 0.3 h. So at different fractions of the height, to get the coefficients of the bending moment. And with this coefficient, you multiply with this factor, you will get the values of the tension. Okay. And for moment, for moments, for different h square by dt ratio of the tank, can get the values of the coefficient for different heights of the tank. So 0.1, 0.2 up to 1 h means full depth of the h. You get the coefficient, and you multiply this coefficient with gamma times x, you get the bending moment. Okay? And this is for the moments in cylindrical walls with circular tanks. So cylindrical wall means tanks are circular and fixed at the base and free at the top. So it is the condition for fixed base and free top. Then and this is the shear force at the base. Okay, so for shear force at the base, triangular load fixed base, rectangular load fixed base. So based on that, you get these tables are given in IS 5370. Okay, and uh, they are based on the same theory which we have gone through. So based on this theory, final based on the final solution, then you can have such tables. Okay, but you can refer IS 2370 part 4 for such tables. But note that the code is not allowed in your examination. IS 2370 part 4 is not allowed in the examination. Just for reference, you can refer and uh, and uh, but you have to go through the theory also, theory only when there is an exam. So we stop here. In the next class, we'll go through the example of circular tank with fixed space, how to design such tanks that we will see in the next class. Any doubt in today's lecture?
Sir. Hello, sir.
So if you don't have any doubt, you can stop here. We'll meet in the next lecture tomorrow.